Now we are going to be looking at the cardiac dynamics and how they change during different intensities in exercise. The cardiovascular system is composed of the heart, blood and blood vessels, which all respond to changes to cope with the demands of exercise. Similarly to the respiratory dynamics, we also have an equation where the variables depend on each other in order to meet the demands. The equation shown on the slide is cardiac output equals stroke volume times heart rate. So in order to calculate cardiac output, which is the maximum volume of blood pumped by the left ventricle each minute, we need to understand and know our heart rate and stroke volume. So our heart rate is the number of beats per minute and the stroke volume is the maximum amount of blood ejected from the heart per beat. It is achieved through ventricular systole, but it's also dependent on the amount of blood returning from the heart and filling the chambers, which is then pumped around the body in order to empty the chambers. Here we also have a table showing the typical values for each component at rest, so moderate and maximal exercise. Similarly with the respiratory values, we can see that as the intensity that our bodies are working at increases, the values also increase. This is due to the fact that the body has demands, which is relying on the heart in order to pump harder in order to transport more oxygen around the body at a faster rate to the target organs like the muscles, and redirect it from organs that don't need it. Within our bodies we have receptors which are responsible for detecting changes in terms of chemical state of blood, and these are known as chemoreceptors. They monitor any changes in oxygen, carbon dioxide and lactic acid. During the start of exercise, the levels of carbon dioxide and lactic acid will increase, and the levels of oxygen will decrease as the muscles are suddenly using more oxygen, so it is depleting in the body. The chemoreceptors detect this change and will send an impulse to the cardiac control center in the medulla oblongata to send an impulse through an accelerator nerve by the sympathetic nervous system in order to tell the body to produce more oxygen. And similarly, at the end of exercise, when the levels of intensity are decreasing, the chemoreceptors will send an impulse back to the cardiac control center in order to send an impulse down the vagus nerve by the parasympathetic nervous system in order to slow the production of carbon dioxide and lactic acid so we can replenish the oxygen. During a warm-up, the muscles release energy which causes the temperature of blood to rise. This results in the heart beating faster to allow more blood and oxygen to be redirected away from the organs, and so the target muscles can have this energy which allows them to be more elastic and less risk of sustaining injury as they are warmed up before taking part in strenuous exercise. Here we have three graphs demonstrating heart rate, stroke volume and cardiac output. So the typical graph showing heart rate, we can see that the person's heart rate is elevated before they actually start working, or they're working at a low intensity. This could be due to an anticipatory rise due to this slight increase in heart rate before the exercise, which could be a result of anxiety or a release of the hormone adrenaline due to anticipating what they're going to be participating in. Some athletes who have better fitness will have maybe a lower resting heart rate due to the long-term cardiac adaptations of cardiac hypertrophy, and meaning that they don't have to eject as much blood in order to, which means their heart rate is lower. Then as the athlete continues to work, they experience a rapid increase in heart rate due to the sudden increase in intensity. This means the bodies are having to work harder in order to meet these demands and to allow the athlete to make performance. We can see that on the graph of heart rate, as the power increases, so does the heart rate. So it's a directly proportional relationship. This also causes a rise in the number of beats per minute and will result in more blood being ejected from the heart, so the maximum amount of blood is increased. This then means the gradient becomes more shallow and the heart rate is still increasing but at a slower rate until the maximum heart rate is obtained. This is known as steady state, where the graph plateaus to show the constant heart rate before then a rapid decrease when exercise stops during recovery. However, this graph doesn't necessarily show, but it's important to know that our heart rate, like our breathing rate, remains elevated and will gradually return to resting over time. This is to allow the body to recover and replenish itself, to remove the excess carbon dioxide and lactic acid and repay the oxygen debt. And as we also mentioned about the chemoreceptors that will send an impulse to the cardiac control center to reduce the electrical impulses sent out through the SA node, so the heart doesn't have to pump as vigorously. This first graph is also looking at how cardiac output changes in exercise, and similarly to heart rate, as the power increases, the cardiac output increases to a certain point. It has a vital role when the body is working at higher intensities in order to meet the different oxygen demands, so supply the target organs with the energy needed in order to stay in performance and to be able to resynthesize ATP. This graph shows that the cardiac output changes as the power increases, so we can identify, as the same as heart rate, there is a linear relationship between these components. But after a certain point, we can see that this gradient begins to slow down and starts to plateau. This is because the cardiac output has met its maximum capacity, and therefore it cannot increase anymore unless one of the other factors increases, like heart rate or stroke volume. One way that cardiac output is increased after its maximum is by the redirection of blood flow. As level intensity increases, the flow of blood is changed drastically as more blood is being carried to the active skeletal muscles. So by sending the blood flow to the skin, it helps to release excess heat and reduce overall body temperature. This then takes blood from the inactive areas, which have a lower demand, to the active areas, especially in exercise which has a long duration and in hotter climates like marathon endurance training, will result to more blood being redistributed to the skin in order to reduce increasing the temperature. However, this means it limits the amount for the endurance, so that to allow the athlete to stay in performance over time and to fuel the skeletal muscles, particularly of the lower body. This is because within our bodies we want to maintain homeostasis at all times. This is keeping the components within the body balanced. This is achieved by the receptors that detect the changes in order to maintain the components so we can keep it balanced. An example of this is the baroreceptors, which help to increase blood pressure if it becomes too low and decrease it when it becomes too high. We will touch on blood pressure later in the video. Now we're going to be looking at the control of heart rate and how impulses are initiated. We briefly touched on the idea that the impulses are sent via the central nervous system, by the spinal cord and brain, to the medulla oblongata, which inevitably initiates the response in order to tell the heart to contract more rapidly or to slow heart rate down in order to meet the demands of exercise. So the impulse will be sent down the accelerator nerve into the SA node. This will then tell the SA node in order to initiate faster contractions to allow the heart to contract as one unit faster, so we can pump more blood around the body. This is an adaptation when the intensity of exercise increases. And as we said, in order to slow down exercise, the medulla oblongata will also initiate a response down the vagus nerve, which aims to slow the impulse or even stop the impulse, so the SA node is not sending out an impulse, so the heart can stop pumping in order to decrease the demands when the exercise is stopped. So the heart doesn't have to pump as rapidly because the intensity is decreased, so our heart rate can return back to resting level. Here are the two graphs produced from the investigations that we conducted in our fitness tests, so the multi-stage fitness test and Wingate test. If we look at both graphs, we can see that the blood pressure increased as exercise went on. So we can see that in the Wingate test, for example, at rest our blood pressure was 116/68, and at the post test it was 138/67, which shows quite a big increase during this test, and this is because as the intensity was increasing, we were working harder. So in order to meet these demands, the blood had to be redirected from the organs that didn't need it to the more target organs, so we could sustain the duration of the 20-second Wingate test in order to cope with the intensity. And similar to the multi-stage fitness test, as we increased the levels of exercise, we can see that our systolic values increased until level 4, and then we saw a slight decrease in our systolic blood pressure levels, whereas in the diastolic blood pressure levels it did increase until same as level 4 at 121, and then it decreased after that. This is showing that because the intensity increased, that's why our blood pressure increased, but until a certain point, this is because when we meet a certain point, our maximum capacity, so our cardiac output met its maximum capacity, therefore we couldn't continue to work at the same rate that we were working at, so our performance is decreased. This can be due to fatigue and the products of lactic acid and hydrogen which cause the body to not be able to respond to the exercise. Our blood pressure also increased, and this is because the resistance to the blood flow is caused by the size of the blood vessels through its travelling. So in smaller blood vessels there is a greater resistance. So by having thicker blood also means there's a greater resistance because it's having to squeeze through the vessels, there's more friction. By changing the resistance to blood flow can alter the blood pressure. So this is achieved by the involuntary smooth muscles in the arterioles relaxing or contracting in order to alter the diameter of the arterioles to make the blood flow more easily or constrict it by vasoconstriction and vasodilation. As a smooth muscle contracts, the diameter of the blood vessel gets smaller, so blood pressure is increased. And on the other hand, as a smooth muscle relaxes, the diameter of the blood vessel is increased, which decreases the pressure of the blood flowing through it. The same principle can be applied to altering the diameter of water. If you place your finger over the opening of a hose, making the diameter smaller, the water will flow out quite forcibly because it is under higher pressure. However, if the water is left to flow unhindered through the end of the hose, it is under low pressure and it will not spurt out due to the fact there is less resistance. As we previously mentioned, baroreceptors measure the changes in blood pressure, and a reduction in blood pressure is detected in the aorta and the carotid artery. This detection is passed to the central nervous system, which sends a nervous impulse to the arterioles to constrict by vasoconstriction. This then increases the blood pressure and has the same effect on increasing the heart rate. When blood pressure is increased, the baroreceptors detect the signal in order to make the arterioles dilate by vasodilation and reduce the blood pressure. Changes to blood pressure during the onset of exercise has the effect of increasing heart rate, which will result in an increased cardiac output and will have the effect of increasing blood pressure. So this is saying that if cardiac output is increased and the resistance of blood flow does not change, then blood pressure would be around 120 over 80 millimeters of mercury, which is the typical value of blood pressure. So baroreceptors aim to inevitably reduce blood pressure when it's high. If cardiac output increases, that blood pressure increases, which is one of the causes, and it can be quite harmful if blood pressure remains at an elevated rate. By increasing the peripheral resistance, which is how easy the blood flows through the vessels, if blood can't flow easily through the vessels, it can lead to conditions such as coronary heart disease, where the vessels can be blocked by fatty deposits, which narrows the lumen, so as the higher resistance when the blood flows through. So this relates to the fitness tests. As we were working harder, we needed more oxygen, and therefore the blood was flowing at a higher pressure around the body in order to meet the target organs and supply them with the energy needed, so we can sustain performance over the more aerobic test of the multi-stage fitness test and the more anaerobic test of the Wingate.